So, welcome to the robot motion planning and control course. I'll try to do it in English, and I want to do some introduction and discuss the course details, what you have to do, what we will going to learn, and then start to work on the first class. I already uploaded the first class notes to the Moodle, and also there are a few other things in the Moodle. You can go ahead and look there. There is the syllabus, I think, yeah. And there is the final work on this course. What you are requested to do in order to pass this course. There is no exam. There is only a final work that you will present in the last two lectures. The reason is that the purpose of this course is to learn. And I hope that in this work, you'll take new things and new research papers or other things that you are doing and present it to all of us that we all can learn from this. So learning from one another. There is a link to a WhatsApp group of the course. You are all welcome to join the WhatsApp group. It won't be extremely busy. You're welcome to post there something interesting that is related to the course. Maybe I'll pass some messages, but it will be quiet most of the semester. So go ahead and add yourself to the WhatsApp group. It's easier for me to communicate with you through WhatsApp than through Moodle. And that's it there. Yes, and you can see already I uploaded all the course notes from last year and all the classes videos from last year. All are there. You can go ahead and learn and advance even more than the classes. All in Hebrew, I'm sorry. Okay, so let's go, let us go over the syllabus. I'll share it with you. Yeah. Screen. It's this one. Now I can't see you from some reason. Can you see the class notes, the syllabus?
Yes. Very blurry.
Quite blurry.
What?
It is blurry.
I'm not sure why. Let's try again. Now?
Still blurry.
אמיר, אתה רוצה שאני אשתף פשוט?
לא, אני רוצה לפתור את הבעיה, אני לא מבין למה. Now?
It's better.
readable.
It's readable?
Yeah.
Okay. Okay, so the purpose of this course is to learn the robot motion planning strategies, algorithms for mobile robots. This is one thing. I'll teach how these algorithm works, how we analyze these algorithms, and so on. And I'll teach also a little bit of control of robotics, stability analysis of nonlinear systems, and how we design controllers for robots. You have here my phone number, my mobile phone number, and my email. You can feel free to contact me when you need something, not only in my short Kabbalah. All the classes will be online. And what we learn? We will learn this semester. We will learn about kinematics of robots, the configuration space, and motion planning. It's not really up to date. I'll start with the bug algorithms, and then graph search algorithms, maps, and then algorithms that distribute the space into cells. And then I think it will be only then motion planning using potential functions. And then we'll go to the second part of the course, which is control of nonlinear systems, dynamics of robots, and Lagrange equations. Then stability of nonlinear system using Lyapunov law, stability of systems with continuous cycles. We're using Poincaré maps, which are not stable, but they have limit cycles. And then we'll do this using something called Poincaré map. Then some control methods for robots like PD controller, robust controllers, sliding mode control, impedance control, and adaptive control. I hope I'll have time to go over all of them. And then maybe I'll talk a little bit about robot grasping. And finally, you'll present your final work of this course. I want to recommend you a few books. So first, there is the Introduction to Robotics by Nir Schwalb. This is kind of a book of the previous course, but it's kind of a background that you need to know, especially in advance, before the second part of the course, the control part of the course. And there are several other books, interesting books. The book by Merli and Sastry is, I recommend it. It's a very good book on mostly mathematical representation of robots. And there is the book by Steve Laval, a planning algorithm, which is mainly about motion planning, and also the book by Jean-Claude Latome about motion planning. So those are the books that I took the material, some materials from each one and compiled it into a course. I want to show you, the final work. I'll go over this not in kind of the middle of the course, but I want just now to give you an overview what you need to do in order to pass this course. There's only one work, and you'll present it in class. So just for you to know, it's already in the Moodle as well. So you'll have to present a research work. It can be a research work from a journal paper like the International Journal of Robotics Research or the IEEE transaction on robotics, or something similar, or a paper from a conference like the International Conference on Robotics and Automation or the IROS conference, or either a book chapter, or it can be even your independent research that you are doing. If it's something related and interesting, we will all want to learn about it. But you have to get my permission to do this work, to select this paper, or to select your research. So just tell me what you want to do, which paper, what is the research, what are the results that you want to present, and get my permission until April 7th. Then I think I already put, I'm not sure if it's new or not. No, this is the old, I'm sorry. The link here is old. I'll update it, but then you'll have to register yourself. Not in this link. I'll open it. I'll open a new link, a new file for that. Do you see my screen?
Yeah, can go.
Oh, Yofi. Then you'll have to write what are the main contributions of this paper, of this research. If it's a paper, then write your opinion of the paper, kind of a review, and describe this. Then you'll have to do a simulation of this research. It can be either in MATLAB, in Python, in ROS, whatever works for you. But it has to be a simulation that describes how this works, have a video of the robot moving, and finally present it in class in a presentation. And then also submit a work, a written work, a report on this work to me. Here, this what the report should be. It can be either in groups of 2 or single student. So this is the work that you will do. Do you have any question about this so far?
I have one question. The lessons will be online. Even the study will be in the university after the Pesach.
I don't have class. אין כיתה, לא הקצו כיתה. So I don't know what will be after Pesach. I don't know if it will be online or not. It's a good question. I don't know really.
Okay, thank you.
It's easier for me to teach like this. It's not. It's worse for you. I know that. But I promise that the classes will be shorter. I won't use all the 3 hours. Okay, any other question? So
Yes, Amir.
yes.
One question. Maybe you can upload an example of research that you aim for.
I'm not sure that I want to do that.
Okay.
Because then all of it will look the same. And I want you to be more creative and do your own work.
Okay, no problem.
Amir?
Okay.
Our report can be English, Hebrew, it's better for you?
Yeah, Hebrew is easier for me.
Okay.
But in class, since the classes will be in English, then the presentation in class would be in English. The report can be in Hebrew, but the presentation, the slides will be in English.
Okay, thank you.
Okay. Oh, I see people are saying that there are students from Tel Aviv University. So we will probably continue online. But we'll see. I'm not sure what will happen after Pesach. Okay. There is one more thing in the Moodle that I put online. I can't find it. But if someone wants to learn ROS, which is Robot Operating System, and it is very useful, you can use this course as an example. I won't teach ROS, but you can learn it by yourself and do the work and the simulation using ROS. It's not easy. I put online some tutorials. Do you see it? So how to learn ROS? It's pretty old. It's Indigo. It's old. I think there are more up to date now. I don't remember which is the current version, the most up to date version. I know many are moving to ROS 2 instead of ROS 1, which is what we have here. But I recommend you to learn ROS. You can do it through the wiki ROS and the tutorials. And there are here all the options, how to learn, what you need to install Ubuntu, to install ROS, to do the beginner's tutorial, then learn about URDF files, which is the file that represent the robot, unified robot description file. You can do it from SolidWorks, to convert files to URDF, and to learn how to use the simulator, the Gazebo simulator. You can do it here. You can see here. Also, you can use the MATLAB symbolic toolbox to calculate some things that we will learn. So this is online. You can learn it by yourself. You can apply it and use it for simulation. It's not easy. It takes time to learn, but you can use it in this course to do this. I promise to give extra points for trying and for using it. It's not. I know it's not easy. So you can use it to learn here. So let's start with the lectures. So the problem of the motion planning problem of robots is to find a continuous path from initial position to final position of the robot through the environment without colliding with obstacles. I want to show you a famous problem called the piano movers problems, which is how to move a piano inside a house. The first solution was given by Schwartz and Sharir in 1983, for a planar rigid body to navigate in an environment with obstacles. I want to show you a short video from YouTube that shows the problem, if I'll find it. It was open a few minutes ago, but no longer apparently. Just a second. Yes. It's here. I'll share it. You can see it from, this is from YouTube. You see the problem here? So you see the pianos. The piano is the black one here, trying to navigate from one point to another inside the house, and then find a path from the beginning to the end of this piano. This is actually a 3D problem, a 6D problem, because the piano can rotate in space. So it can also change position in X, Y, Z, and rotate in roll, pitch, yaw, and then move along the house. Schwartz and Sharir solved it in the 3D problem, which is only the piano is on the floor and can only move and turn on the floor, which is a little simpler because the search space is in lower dimensions than the 6D dimensions you can see here. You can see here several algorithms that solve the problem in various ways. So all of them can find a solution. Some are takes longer, some takes less. Some algorithms here are probabilistic.
Amir,
Yes,
it is search problem or it's learning?
it's search problem. It's not learning.
Okay.
They search for a path. If it was learning, they had to have an example. Here they don't have an example.
And it's not optimal. It's optimal guarantees or not?
Schwarz and Sharir solved, I think their solution was optimal. Here it's not optimal. Here it's a solution, it's not this solution.
Oh, okay, thank you.
Yeah. Yeah, I'll stop share. And I'll go back to, I'll go to the lecture note. And I'll share this with you. Can you see it? So I told you about the motion planning problem and the problem, the piano movers problem. And now let's talk about control. In the control problem, we have a robot. We have a control system that actually controls the position of each joint of the robot, or the position of the robot. It actually applies torque to the wheels or to the joints of the robot. Then we have some sensors that sense the environment, sense the robot state. Sometimes we have an estimator that estimates where the robot is. And this goes back as a feedback to the control system to feed the robot with the desired torque or force to move the robot along the required trajectory. Also, it is fed back to a motion planning algorithm, which is the higher level planner that plans what is the path that the robot should go along. And this is fed into the control system. And on top of this, there is a mission planning, which plans the entire mission. Sometimes it's not only going from one plan to another. You have to take something from one plan to put it from one point to put it in another point. So you have a mission planner on top of it. So we have actually three levels. The lower level is the control level. The upper is motion. The middle level is motion planning. And the upper level is the mission planning. This is how we plan a control system of a robot. In the motion planning problem, which is the middle level, we want to provide the robot with a command in a higher language that the robot will then the robot will plan its motion automatically in order to conduct this mission to do what the command says. So some example to missions, to robots missions, it can be either motion planning to move from one point to another. It can be exploration, to explore the environment, to see what there is in the environment, to go to an unknown places and search them. and it has to be motion planning while avoiding obstacles. It can be area coverage. We want to do this in this course. There are several papers that are dealing with area coverage. Maybe someone would like to do a kind of the final work on area coverage, where we need to pass a sensor or a tool along all the points in the workspace. This is the meaning of coverage. You want to cover the entire area with a tool or with a sensor that sees the entire area. It can be a localization, to know where the robot itself is, to find the configuration of the robot in space or in the plane. So this is another important and interesting mission that is done, which is required for motion planning mainly. Outside it can be GPS. Inside we need other sensors like LiDAR, laser scanner, or something like that. And it can be mapping. If there are obstacles in the area, we want to build a map of the area to see where the obstacles are and to allow navigating inside the map. And we can do some of those missions together simultaneously. This is called SLAM, simultaneous localization and mapping. So usually we would like to have a mobile robot that is moving in an environment in a map. And while moving in the map, it builds a map of where the obstacles are, and automatically at the same time find where it is in this map. This is called the localization problem.
Amir, I have a question. What's
Yes.
the difference between mapping and coverage?
Mapping, you don't have to cover you don't have to cover the entire area. You can build a map which is not full. And coverage, you usually want to pass some tool along the environment, something like vacuum cleaner in your house, and you basically want to cover all the floor when to clean it. While mapping, sometimes it's enough to see, and you don't have to see all the environment. You map only the area that you find along the way. In coverage, you want to find all the environment, to cover the entire environment. That's okay?
Yes, thank you.
I want to talk a little bit about properties of the robot. This is kind of an introduction, just to have to all of us to speak the same language, the same terms. So with regard to the structure of the robot, there is the number of degrees of freedom, and there is the workspace where the robot is working, and the configuration space, which I'll describe along the class today. So I won't go over it now. There are some constraints for the robot. Sometimes the robot cannot move in all directions. Sometimes it can move in every direction, And these are called omnidirectional robots, omnidirectional wheels. Then the robot can provide speed or move in any direction. But if it cannot provide velocity in any direction, and there are some constraints, like in our car, that we cannot park sideways, we cannot move sideways in order to park the car, we have to do some maneuver in order to park the car. Because we have some constraints, the car cannot move, cannot drive sideways. This is called a non-holonomic constraint. This is a constraint on the velocity of the system. We'll talk a little bit about holonomic and non-holonomic constraints in the control part of the course. And there are some models for systems, for robots. It can be a kinematic model. In kinematic model, we describe only the motion, only the position and velocities of the system. We do not deal with inertia, with forces, and so on. Just kinematics, just the position and velocity of the system, of the robot. And can be a dynamical model, which we deal in control, where the inputs to a dynamical system are usually the forces and torques to the motors, and then there is the inertia and the gravitation and everything that and all the equations of motion as we learned in dynamics. So it can be a dynamical model. I'll show you the dynamical model of robots in the second part of the course. So now let's start with the first part of the course, the motion planning part of the course. And in motion planning, we deal with algorithms that navigate the robot from one point to another. And those algorithms have several properties. It can have several properties, and that I want to talk about it. First is optimality. The algorithm is better to be optimal. It should solve the problem in an optimal way. It can be optimal in terms of the length of the path, in terms of the time that it takes to go from one point to another, or in terms of energy consumption along the way. So we can define different cost functions and design different algorithms that will be optimal for different cost functions. We can talk about complexity, and it is about computational complexity. Computational complexity is a measure how good the algorithm is, how good the algorithm performs. And it can be how much time it takes to do the search. It can be any kind of how many computations steps we need, and so on. And we can do it, we can compute the computational complexity of an algorithm in the worst case scenario. So if we can think of a scenario that is most difficult for the algorithm to solve, and this will be the worst case solution, and there we can, this is a kind of a measure to compare some algorithm, how they deal in this worst case scenario. And now it's more, I'm not sure more common, but it's common also to compare the average case. So run the algorithm on many different cases and see how much time it takes to solve the problem in the average case, on average between all the different cases. So after we talk about the computational complexity, we want to talk about complexity of memory. How much the algorithm can use either a constant amount of memory. It can be polynomial in the size of the problem. If I have a space which is 1 kilometer by 1 kilometer, it will be amount. It will be a certain amount of memory. But if it will be 10 kilometers by 10 kilometers, then it will be 100 times more. This is linear, or it can be a polynomial. But in the worst case, not in the worst case, but in a bad case, it can be exponential. Then as the problem grows, the amount of memory that I need grows exponentially, and then I can solve only small problems, and I cannot scale this up. So this is another thing that we have to consider when dealing with algorithms, is how many computations it takes and how much memory it takes to solve the problem. And all with respect to the size of the problem. We want to talk about completeness. An algorithm is called complete if it will always find a solution when such a solution exists, or it will say that there is no solution when there is no solution exists, and it will tell this in a finite time. It won't search forever for a solution, even if there not exists a solution. So if there exists a solution, it will find it. If there is no solution, it will stop and say there is no solution in a finite time. Algorithms can be either solve the motion planning algorithm either offline or online. Offline, when the computation, the search is done a priori before starting to move. It's done in the computer in advance. And online, then when the robot is building the plan, the motion planning, gradually during the motion, during movement. And this is also called a sensor-based motion planning, the online problem. Some notations. We say the workspace will be W. Usually it's either R2, R3 in the plane, R2 in the plane, R3 is a three-dimensional space. And it can be this is the space, and this is the plane. So this is W, and sometimes we have obstacles in the workspace. So the notation for them is WOI. This is workspace obstacles. I is the ith obstacle. And the free space, W3, is the workspace W, not including all the obstacles. So this is the uniting all the obstacles, and we take the workspace minus these obstacles. This is the free space. Now I want to talk a little bit about configuration space, what it is. So say we have a robotic arm. Here you can see a two-link robotic arm in the plane. We have two joints, theta1 and theta2. Those are the angles of the two joints. And you see here the workspace. It cannot go beyond this point because this is the minimal radius that it can go, and it cannot go further from this radius. This is the maximum radius when the arm is fully stretched. And this entire area is the workspace. This is in plane, this is the workspace of the robot. But in this workspace, I have an obstacle. You see here, this is the obstacle, the blue one. And this is called WO1 in this case. So this is the workspace. I can look at the configuration space. The configuration space coordinates are the parameters, the configuration parameter of the robot. Here is it's theta1 and theta2. It's the degrees of freedom of the robot. So this is the first configuration, coordinate theta1 and theta2. And here, each point here is a certain position of the arm. So I can map the workspace here for all theta that I can go, that the robot can go, and I can map the obstacle to all points, all configuration in which the robot hits the obstacle. As you can see here, in a point here inside this obstacle, this is theta1 and theta2 such that the robot hit the obstacle. I can look at this also in a topologic way, because theta1 and theta2 are not Cartesian coordinates, because when I hit 360 degree, this is exactly the same as going back to 0 degree. So it's kind of cyclic coordinate. So I can look at this as one cyclic coordinate theta1, and the second cyclic coordinate on top of it, theta2. And it looks like a torus, as you can see here, like bagel, like a bagel, yeah, like a torus, as you can see here. And the idea is that the coordinate theta are cyclic. They can go 360 degrees. Sometimes in robotics arm, there are some limitations, and some joints cannot go 360 degrees. They can go less. And then I can map all the workspace, and it's not a torus. Any question on that?
Yes, this bagel representation of theta1 and theta2, it's the obstacle space?
No, this is the workspace.
Okay.
It's not the obstacle representation. It's just the theta2, theta1, and theta2. It's kind of topology, how to see it, because this is a cyclic coordinate.
So the hole in the middle is the obstacle space?
No, there is no, the hole in the middle is nothing. There is nothing there because I can change only theta1 and theta2.
Okay.
I can go only on the boundaries of this torus. It's not something real. It's just how to think about it, how the configuration space actually looks like, because I can draw it in like a Cartesian coordinate system, but it's not really a Cartesian coordinate system, because when theta 2 goes to 360, it actually goes back to 0. And I cannot draw this here in a Cartesian way, because there is a cycle here. Do you understand?
I'm not sure, but I'm trying to get some sense out of it, and maybe it's too early.
For every useful thing, we use this representation, the Cartesian way.
Okay.
And this you understand, right?
Yes, sure. Yes.
Okay.
Amir, I have one more question.
The topology is just to show that this coordinate is cyclic, but it's just תרגיל מחשבתי. It's just for our thought. It's not for something useful now.
Okay. Okay.
Not
Thank
in
you.
this course.
Amir, so in configuration space, it's
Yeah.
not include the obstacles, only the workspace, representation of the workspace?
No, the configuration space have the obstacle. So I map all the points, all the configurations, the collections of theta 1 and theta 2, in which the robotic arm hit the obstacle. And
Okay.
this is the configuration obstacle, and we represent it as QO. Q is the configuration space, and O is the obstacle, configuration obstacle.
So in the torus example, we don't see the obstacle, only in the Cartesian.
No, you don't see it here.
Okay.
Maybe some parts of the torus we have to take out, which are the obstacle.
Okay, thank you.
Amir,
Yes.
you drew the obstacle like a circle in the left figure. Does it mean that it's necessarily going to be a circle and
it necessarily won't be a system.
Won't be, right? Yeah. So it's not like an accurate.
No, it's not. It's not even close to something similar. Usually.
Thanks.
And note that if the arm has 3 links, not only 2, then the workspace would be 2-dimensional, because this is still in the plane, but the configuration space will be 3-dimensional because we have 3 links. You understand?
Yeah.
Okay. So I talked about configuration space. Now the definition of a robot. Robot is the set of points in the workspace which the robot takes, covers actually, when it is in a configuration Q. Q is the position and orientation of the robot. Now I'm talking about mobile robot. You can think about a mobile robot. It can be mobile robot as I draw it here as a triangle, and it moves in a X and Y plane. As you can see here, and the robot itself has a position and orientation. So I can have the position of the robot X, Y, and also the angle of the robot with respect to, say, the x-axis. This angle would be theta. So this is the configuration of the robot. It's x, y, and theta. The configuration of a robot in, and say, a plane XY plane workspace. So the robot R of Q, R of X, Y, and theta are all the points that the robot actually covers. And a configuration space, a configuration obstacle, is all the configuration Q in which the robot intersects an obstacle in the workspace. Where the intersection is not empty, this is where the configuration obstacle is. Is this clear or not? I lost you?
Yes, yes, clear.
Yes, it's clear.
Okay. Yeah. Oh, what happened? Yeah. Okay. And the free configurations are the whole configuration space minus all the obstacles, the configuration obstacles, as you can see here.
What is UI? UI.
U is unite, is ichud. This is chituch, the intersection.
Yeah.
And this is unite ichud of
But before
unite
before
all the
ichud,
obstacles.
Before ichud, there is a sign of pachot, no?
This.
Okay.
This takes the whole space.
Okay.
And from this whole space, I subtract all the configuration obstacles. So this is one configuration obstacle. The unite is all the configuration obstacle, and then I subtract them from the configuration space. It's like a big U is to unite thing.
Like sigma.
So let's talk about a trajectory, a path in the configuration space. So a path, we call it C, maps numbers, actually scalar, from 0 to 1 into a continuous path in the configuration space. It has to be continuous, a continuous path. It cannot be broken. It can have sharp edges, but sharp vertices, but it has to be continuous. It starts in the beginning, in the scalar 0. It started at the start configuration, and it ends at 1 in the end configuration. And C of S is a point along the path. Just a second. Is a point along the path which belongs to the free space in the configuration space, where S is a parameter that moves from 0 to 1. Yes. Yes, there was a question.
maps from 0 and 1, but 0 and 1
from
is
no, it's the Ketites,
Yeah, it's a range, but
it's a range from
it's
0
not a
to 1.
scalar, it's floating point. No,
it's a scalar, yes, floating point, yeah. It's not a vector.
Okay.
That's the meaning of scalar, yeah. It's a floating point, something like this. Yes, it's a number. Between in the range of 0 to 1, including 0 and 1. You see it, the set here includes the edges, the boundaries. It includes both 0 and 1. It's a closed set of points. Okay, so now I have a problem, a motion planning problem from one point to another in space, in the say configuration space, and if my configuration space is the plane, and I want to travel from one point to another in the plane, and my robot is just a point and has only a position sensor, and it has a sensor, a touch sensor that touch when it hits an obstacle, and also my workspace is closed and it's finite, it's not infinite. Then there is an algorithm called bug1. Then I'll show you the bug2 algorithm that plan the motion from one point to another along this space. It's very simple. Algorithm bug1 takes as input the start position and the output, and the still the input, the start position, the end position, the goal position, and it gets also a robot with a touch sensor and a position sensor. And the output is a path, a continuous path from the start to the goal, or a conclusion that such a path does not exist. How it works? It's very easy. It starts from the start. I'll show it. I have it here. And then I'll show it how formally we write it, but I'll explain it on the drawing first. So I start from the start position, and there is the goal position. I go towards the goal. I want to go along a path towards the goal. Then when I hit an obstacle, I start and go around this obstacle, go all the way around the obstacles until I finish a complete circle around the obstacle. When I finish the circle, I find a point along the boundary of the obstacle, which is closest to the goal. So this point is the closest to the goal. I go back to this point along the shortest way around the obstacle. And from here, I go directly to the goal. I go directly to the goal until I hit another obstacle. When I hit another obstacle, I go around all these, the obstacle until I finish a complete cycle around this obstacle. And then I find where the point along the obstacle boundary, which is closest to the goal. This is the point. And I go along the shortest side of the obstacle to this point, along the boundary of the obstacle, and then go to the goal position directly. This is the idea. This is how it works. Very naive, very simple. This is called the bug algorithm because it's like a bug go directly, and when it hits an obstacle and fill the obstacles, then it goes around. I'll go and tell you how we write it as a formal algorithm. So this is the initial step. In the initial step, we set Q0 leave. L is the leave point, is the start. And then in the ith step of the algorithm, this is done continuously. So in each step of the algorithm, we go from the current leave point along the line that connects the current leave point and the goal until we hit an obstacle. When we hit an obstacle, we mark this point as QIH. H is the hit point. If the hit point is the goal, then stop. You reach the goal. If not, you go around the obstacle, and while doing so, you measure the length that you travel along the boundary of the obstacle from the hit point and up to this position. And you save the the closest point to the goal. If you search for the closest point to the goal, and if this is the closest point, you save it as Q min. If not, then you don't save it. You continue to go. And also you measure the distance that you travel from the Q min that you measured to the current point.
How I measure this one? 2.3.
You know where you are at each time, at each instance. So if you know where you are, you can do small steps and count them, how much you traveled from the last point that you were in each iteration.
But I traveled only in one direction, so I make
No, you travel along the boundary.
But in one direction, right? For example, if I travel from up till down.
No, if I'm going here,
yes,
there is one point, and then I'm in after a second I'm in another point, so I can measure how much I moved. And
so how the bug knows to move like a blue line? No.
Because I measured, I know where the Q min is. I measure the distance from Q1H.
Exactly. You measured it exactly this direction, not
this direction. Yes. But if I'm here and I measure this direction and I know from here to I know the whole direction, the whole circle.
Yes.
How long it is? I know how much how long it will be from this side, and the whole circle minus this will be how long it will be from the other side.
So it does this action like one minus another.
Yes, of course. Okay. This is how you compute it. And when you you end this circle, this cycle, you go back to Q min. This is the blue point. The blue path. You go back to Q min along the shortest path of the boundary, along the boundary of the obstacle, and then you set the new leave point at Q min. This will be Q leave 1. You see, there was Q hit 1 and then Q leave 1. If you can leave QL along the line that connects QL to Q goal, along this line. Then you go back to 1 and continue all this from the beginning as we did here, and you go to the next obstacle. If not, if you cannot leave this, and I'll show you when you cannot leave, then stop, because there is no solution, there is no path to the goal. And I'll show you where this happens. If the start is inside this closed room, closed circle, and the goal is outside, so there is no solution. I cannot go from start to goal because it is closed. Then it will go to Q. It will go from Q start to Q goal along the path, the line that connects them. Then go around the obstacle, find this as a Q leave, but it cannot leave. It cannot leave along the line between Q leave to Q goal, and therefore there is no solution. That's the problem.
How it knows to check if it cannot leave or it can leave?
If it can leave along, because it builds a line. It builds a line from this point, Q leave, to Q goal. And it tries to travel along this line. But it cannot travel along this line because it hits the wall.
Okay.
Therefore, it's stuck. In the worst case, the bug algorithm travels this amount. It's the distance between the start and goal, the minimal distance from start to goal, because it goes along the shortest line, the shortest path. But to this, we have to add at least 1.5 times circumnavigating all obstacles. So it's the sum, 1.5 times sum the circumference of each obstacle. And this is the amount that the bug algorithm will go. So there are several theorems, claims here. One is that the algorithm stop at each workspace which is bounded. And the idea to show this is that the algorithm does not go back to a boundary of obstacle that was left. And since there is a limited number of obstacles, then and the limited amount of boundaries, then it will stop eventually when it will cover the entire obstacles boundaries, and it will pass each boundary at most 1.5 times. And therefore, there is a limited number of boundaries in a limited length of boundaries in a closed environment.
Amir,
closed workspace. Yes.
Why is the length it's small than what it's right and not equal? Because it always do 1.5 length of the obstacle?
It's always this, but for this it can be shorter because some of it is along the way in the obstacles. So you take less than the lines here, the direct lines are shorter than the full line from start to target, because some of this line are inside the obstacle.
Okay.
This is the reason less. The idea, the second thing is, the second theorem is that if there exists a path, the algorithm will find it. And the idea is that the distance we represent the distance of Q is the distance from a certain position. Q is the XY of the robot to the goal. It's the distance. It's actually a norm here of the vector between the current position and the goal position, minus the goal position. So this is the distance to the goal, and the distance is greater than 0, and the distance at the goal is 0. And the idea is that we have we start with Q leave, then hit an obstacle, then Q leave again, and then hit an obstacle again, and so on. And the distance is already getting short, all the time is getting shorter. Otherwise, we won't leave. We'll go back to the same position and say there is no solution. If there is a solution, each time we leave an obstacle, it's in a smaller distance than the point that we hit the obstacle, and therefore the distance is going shorter and shorter along the time. It's the other way, shorter and shorter. No, this leave is greater than this, and the distance getting shorter and shorter as we hit and leave obstacles. And since we have a limited amount of obstacles because the workspace is finite, then there is a limited number of couples here, like hit and leave, and then it will get shorter every time, and Q leave, the last Q leave will lead to the solution, to the target. This is the main idea, how to show it. That if there is a solution, the algorithm will find it, because it will get shorter and shorter. The distance will get shorter and shorter until it will be 0. So this is the bug 1. But bug 1 is, you see, it's kind of not efficient, because you go around and then you go back. This is kind of not efficient, and therefore there is another version of the bug algorithm called bug 2. And bug 2, I'll show it to you, and then I'll show how it works, the formal way. So the bug 2 starts from start and then go to the goal. But here we draw a line from the start to the goal, and we go along the line until we hit an obstacle. Then we choose a direction, any direction. It can be either right or left, then go around the obstacle until we hit the line again. When we hit the line again, we go along the line until we hit another obstacle, then we go around the obstacle again from one side, not the other, and then go to the goal. And in this way, we don't go 1.5 times along the boundary of each obstacle. This is the main idea of bug 2. So what we are doing is, so M is the line that connects Q start to Q goal. We start with the first leave point would be Q start. And then in the ith step of the algorithm, we move from M, along M, from the previous leave point towards the goal until we hit an obstacle at Q hit. If the Q hit is the goal, we stop, we reach the goal. If not, we turn, in this case, right, but it can be either left, but be consistent only to one direction. And then follow the boundary of the obstacle until you reach Q goal, then stop. If not, if you reach Q hit, there is no solution. You went around all the obstacle and you didn't find the line again. You cannot leave. So there is no solution, there is no path. If you hit the line M again at a point P, such that the point P is not the hit point, and also the distance to the goal at P is smaller than the previous hit point, then you mark the P point as the new leave point. And then if you can leave, if you can go towards the goal from the new leave point, then go back to 1 and leave it, leave the current obstacles and go to the goal. If not, there is no solution. And this is the example that I showed you. I want to show you here a more complex example. If I go here, and this is the blue thing is the obstacle, and I need to go from start to target to the goal. Then I'll go from here with the red. Here I chose to go left at each time, so I go left, I go here, I hit the line again, then I'll go here, I find another obstacle, I go left again, I go back along this, as you see here, go all over again until I won't stop here because I already was here and this is not closer. I didn't get closer to the obstacle, so I won't stop here.
Why you don't stop here? Because in the algorithm?
Because the algorithm says that the leave point P, the distance to the goal has to be smaller than Q hit. And Q hit was here. So the distance here is larger than here.
Okay, thank you.
So I won't stop. I continue to go along the boundary. I go along the boundary and until I hit the line again. When I hit the line again here, I go directly to the goal. So a little analysis of the bug algorithm. I mark n is the number of times that the M line passed through the obstacle boundary I. Inside a disk, which its radius is B is the ball, is ball, which is centered in Q goal, and its radius is the distance between start and goal. So this is the number of times that the line M intersect the boundary of the obstacle between the start and goal. And the length of the path that the robot will pass is, at the worst case, it will go over the boundary of the ith obstacle at most half the times the line intersect the boundaries. If it intersects twice, then we'll go at most, if the line intersects twice, then we'll go around the entire obstacle at most. And why the entire obstacle? Because the line can be at the end of the obstacle. So at most I have to go over the entire boundary of the obstacle. So I have half the n times.
How can it intersect once?
What?
How can it intersect once and not twice? It's always twice, will be, no?
Yes, and therefore there is half here.
Okay. So why just not write the
number of obstacles?
Yeah.
Because it does not necessarily intersect, go over all the obstacles. It's just the obstacles that intersect the line. If there is another obstacle here, then it doesn't matter.
Okay.
So there is when the robot hits, it follows the boundary at most one cycle along the obstacle. And the number of hitting points at the boundary is at most half ni. One is n has 2 points. One is the hitting point and one's the leaving point. So half the times it hits, the number of hitting points is half the n. And the length of the path is the distance from the start to goal, is at most the distance from start to goal, and half the number of the hitting point between M and the obstacles, and the circumference of each obstacle. So this is how long it takes to pass along the obstacle boundaries, and this is the distance from the start to goal. And this is the maximal distance that the algorithm will pass. You see, even though it is shorter here, it looks here it looks shorter than bug 1, but the boundary, the upper boundary of the length that the algorithm will go is longer than the bug 1, because in bug 1 I have here 1.5 times the obstacle, the 1.5 obstacle boundaries, and here I have ni over 2, which can be much longer, much bigger than 1.5. So the boundary here, the upper boundary of the length is less tight than bug 1, because in worst case this can be more, as I showed you here. It can be, in worst case, it can be more than 1.5 times. That's it for today, I think. Yes, it was long. Next time we'll go and learn about more advanced algorithms, motion planning algorithms. That was just an introduction, and we'll go over more interesting things. You have here my email, and you have my phone number in the syllabus, and you have the WhatsApp group. And that's it. If you have questions, you can ask.
Thank you. Bye.
Anyone has questions? Okay.
No? Thank you.
I'll see you next week. So goodbye for now.
Thank
Thank
you.
you.
Goodbye.
Bye. Thank you.
Thank you.
Bye.